Common natural disasters have been a fact of human life since the beginning of time. The natural forces which make life possible on Earth also have enough power to transform our world drastically. Landslides, tornadoes, floods, lightning, wildfire, tsunamis, hurricanes, earthquakes, volcanic eruptions. The continental United States has had its fair share of natural disasters, but most pale in comparison to what is coming next. From the spinning hurricanes of the Gulf Coast, to the menacing storms of Tornado Alley, to the shattering earthquakes of California, the United States is no stranger to deadly phenomenon. Perhaps even more alarming, it is home to 11 of the world's deadliest volcanoes. When the word volcano is even mentioned in the context of the North American continent, most people's minds automatically go to the supervolcano that's located in Yellowstone National Park. Yellowstone is one of the oldest, largest, and most famous parks in the world, graced with over 10,000 thermal features, and home to an abundance of flora and fauna. It is the most monitored and studied place in the world, but hasn't had a major volcanic eruption in 630,000 years. But is this Yellowstone eruption theory, in fact, a distraction to the real danger at hand on the western coast of the USA? The Cascade region of the northwestern coast of the USA boasts 11 of the 18 most dangerous volcanoes. Yet the fervor over a Yellowstone explosion overshadows that very real threat of Cascadia. What really is the greatest natural threat to the USA? Tourists and rangers wander the Yellowstone boardwalks. Animals gather at the sides of the roads, mingling among the thousands of geothermal geyser pools. That's 60% of the world's geothermal features. This is the Yellowstone everyone knows. Most people who visit Yellowstone are blissfully unaware that they are standing on top of an active, breathing volcano. They visit geysers and hot springs, and may even feel some of the numerous earthquakes that rattle the region. Do they realize the seemingly solid ground beneath them is slowly stretching apart and huffing and puffing upward and downward? Are the visitors aware of the large chamber of molten and partially molten rock several miles beneath their feet? Or of even the deeper plume of hot rock moving up from deep within the earth? Indeed, it's easy to enjoy the national park's geysers and other scenery without stopping to consider they're merely the uppermost visible part of the world's geological wonders, the Yellowstone hotspot. All the geysers, hot springs, steam vents, and earthquakes at Yellowstone today are only minor reminders of the last 2 million violent years of cataclysmic caldera blasts. Extensive lava flows, and explosive steam eruptions. Scientists have been studying Yellowstone to understand its activities since the park's establishment.
Well, Yellowstone is one of the best monitored volcanic systems in the world. There's a really comprehensive array of seismic stations. There's a couple dozen GPS stations that are tracking how the ground is moving. And the neat thing about Yellowstone is that it is so dynamic. It's always changing. Personally, I find the Norris Geyser Basin to be among the most interesting spots, and that's because it seems to behave a little independent of the caldera. So Norris is just outside the caldera, and the caldera has these ups and downs, and Norris has ups and downs as well that seem to be somewhat independent of what happens in the caldera.
Volcanism, earthquakes, movements of tectonic plates, and other geological processes are key elements in shaping the planet's landscape. Yellowstone, the nation's first national park, was sculpted both by these forces and by the Yellowstone hotspot, a source of heat and molten rock with roots deep within the earth. The unusual hotspot is tied directly to catastrophic large eruptions.
Well, Yellowstone certainly does have big explosions. It's had 3 over the last 2.1 million years. But it also has lava flows. There's many dozens of lava flows that have happened, especially since the last eruption, that have filled up the caldera. There's also hydrothermal explosions, basically where the hydrothermal system superpressurizes and you get water flashing to steam underground. And in fact, some of the largest hydrothermal explosions known on Earth occurred from Yellowstone, especially on the north side of Yellowstone Lake. So that's the most likely form of activity to happen. Norris is also the site of the largest geyser in the world, Steamboat Geyser. And over the last year and a half or so, Steamboat's just been going nuts. It's erupted dozens of times, and it's a spectacular sight to see. So I'm a big fan of Norris. I think that's a spectacular spot. But the neat aspect of Yellowstone is you kind of can't go wrong. There's so much going on there. And year to year, it's different, just because of the dynamic nature of the landscape. So it's difficult to go wrong in Yellowstone in terms of your favorite spot for neat volcanic and magmatic and hydrothermal activity.
People call it the supervolcano, but I prefer to call it a giant volcano. They're super eruptions, but not super volcanoes. So we call it, so it's truly a giant volcano. And these are these giant calderas, which there's about 30 in the world. Most of them are in oceans, along oceanic trends. Hawaii, Iceland are giant volcanoes along ridge crests, and they're the famous ones. So Yellowstone is a hot spot, more or less in the middle of the North American continent. So it's very unique. So the magma that's erupted at Yellowstone is different than the magma erupted in ocean settings. And that's what makes it so unique in terms of both its size. It is a giant volcano, and it's had 3 major giant eruptions, the first at 2 million years, one at 1.6 million, and the last one 630,000 years ago. Well, those are the ones people hear about, but they are truly giant eruptions. They erupt 600 cubic kilometers of magma, but in between, and since the last super eruption, giant eruption, we've had about 60 to 70 volcano eruptions, like the size of Mount St. Helens. And so the topography of Yellowstone is really the remains of these younger eruptions, which are as young as 70,000 years in the southern part of Yellowstone, the Pitchstone Plateau, for example. That's 70,000 years old, and that's the last volcanic eruption in Yellowstone. And since then, we've had, of course, a lot of hydrothermal eruptions, and that's what Yellowstone's danger is primarily from.
The northern half of Yellowstone Lake lies inside the volcanic caldera. It hosts more than 250 hydrothermal vents and dozens of explosion craters that are hidden from view on the lake floor. Though difficult to access, this hydrothermal system provides an ideal natural laboratory to study the relationships between tectonic, magmatic, climatic, and hydrothermal processes. In fact, the northern part of Yellowstone Lake hosts the largest known hydrothermal explosion crater in the world, known as Mary Bay. The 1.5 mile wide crater formed nearly 14,000 years ago. This type of small but still explosive eruption can occur from shallow reservoirs of steam or hot water rather than molten rock.
The last decent-sized hydrothermal explosion happened over 1,000 years ago, so even those aren't spectacularly common. But because we have such an active hydrothermal system there, hot springs, geysers, and so forth, that threat of water flashing to steam is sort of ever present. And it happens actually pretty often, every year or two, to a small scale. So you can get these small explosions pretty frequently at Yellowstone. But fortunately, unless you're standing right next to it, it's not going to do that much damage.
The hotspot produces volcanic activity, ranging from hot springs and geysers to cataclysmic eruptions. The beauty of the region helped inspire the global environmental ethic, and its geology has revealed new ideas on volcanism, active mountain building, earthquakes, and glaciation. This is all happening in what is referred to as a supervolcano, located smack in the center of the USA, and continually bubbling and steaming. There is constant fervor over the big blast and this great volcanic area releasing a giant explosion, otherwise known as the Big One.
The supervolcano term, I guess I'm not a huge fan of, because it tends to sensationalize something that's already spectacular, and it doesn't need this push to make it seem scary. It lends this idea that Yellowstone only ever explodes, which is not true. Most Yellowstone eruptions are actually lava flows. In fact, the reason you can't see a big crater at Yellowstone right now is because it's been filled with all kinds of lava flows that have happened since the big explosion, which was 630,000 years ago.
This is the most studied volcanic area in the world, but fear of explosive eruptions overshadows other real threats in the United States today.
I haven't mentioned earthquakes, but Yellowstone is probably the most seismically active area in the interior West. The Hebgen Lake earthquake in August of 1959 ruptured in about 11:30 at night. And it produced a fault scarp on the north side of the West Yellowstone Basin. And a fault is where the offset of the ground, as the valley goes down, the mountain goes up to 22 feet of offset. So the valley of West Yellowstone dropped 22 feet compared to the mountain block. And of course, it shook the whole area of the interior West, but the actual shaking of the ground caused a lot of landslides. And the landslides are what ensued in the death of 28 people, primarily from big rock slides coming down in the Madison Canyon. So the Hebgen Lake earthquake was a very important earthquake, and we do earthquake hazard analysis quantitatively. So we calculate the earthquake hazard of the whole Intermountain region. And by the way, we're part of the Intermountain Seismic Belt. The Intermountain Seismic Belt goes from St. George, Utah, all the way to Kalispell, Montana. So it's a zone of earthquakes that really wasn't recognized until the 70s. Everyone paid attention to the San Andreas. But now we notice this was a separate continuous belt. And it's had some large earthquakes, including the Hebgen Lake earthquake, including the 1983 Blora Peak earthquake, which was a magnitude 7. And we've had lots of magnitude 6s in Montana, Wyoming, and Utah. So this is a very active area, and the Teton Fault, for example, bounds the south side of Yellowstone, and the Hebgen Lake Fault bounds the west side of the Yellowstone volcano field.
The Hebgen Lake earthquake continues to be the largest earthquake to occur in the U.S. Intermountain West in historic times. The area around Yellowstone and much of the western U.S. is earthquake country. Earthquakes happen nearly every day in the region, and occasionally the area produces strong earthquakes that are capable of affecting large areas and causing damage. We should expect similar effects if another earthquake of this size would happen today, except there are many more people visiting the area today than there were in the summer of 1959. The more we are prepared for earthquakes, the better we will be after one happens. A bigger and more immediate threat lies 1,000 miles southwest of Yellowstone National Park and is widely considered to be the home of the next big one. The massive San Andreas Fault Zone is the boundary between the Pacific and North American tectonic plates and runs more than 800 miles from San Francisco to the Salton Sea east of San Diego. On April 16, 1906, the Great San Francisco earthquake struck without warning and became the most catastrophic event in the West Coast history. It caused a rupture in the land that stretched for 296 miles. The quake and massive fire that swept through San Francisco killed more than 3,000 people and left over 225,000 homeless. Scientists recently had predicted that there is only a 22% probability of a 6.7 or larger magnitude quake hitting the San Francisco or Los Angeles areas by 2043. But on the evening of July 5th, 2019, a magnitude 7.1 quake hit near the city of Ridgecrest, California. It was a disturbing reminder that the USA faces a catastrophic major earthquake sometime in the near future. Forget the Yellowstone supervolcano and California earthquakes. Just north of the famous San Andreas Fault lies a tectonic time bomb, the Cascadia Juan de Fuca subduction zone. This vast region threatens violent megathrust earthquakes, catastrophic tsunamis, and contains a potent collection of volcanoes known as the Cascade Range. There is no force on Earth quite like a subduction zone. Slips along these faults, found where plates of dense ocean crust dive beneath continents, cause the world's most destructive earthquakes and tsunamis. A giant megathrust earthquake just like the one that hit Japan in March of 2011, threatens America's Pacific Northwest. A huge area from Northern California all the way to Canada is at risk, including major cities like Seattle and Portland. Cascadia is part of the Pacific Ring of Fire, home to the world's most active volcanoes and quakes. Since 2004, 3 major regions of the Pacific Ring of Fire have been hit by quakes greater than magnitude 8. A 4th region, the Cascadia subduction zone, runs more than 600 miles along the northwest coast. The source of all this danger lying underwater of the Pacific Northwest coast is a huge gash in the Earth's crust, a subduction zone. The Earth's crust is made up of huge plates of rock that are constantly in motion. Where 2 of these giant plates meet head to head, one of them can get pushed down under the other. It's here where strain is building up as the Juan de Fuca plate struggles to push beneath the North American plate. When it releases, it will trigger a region-wide earthquake that will shake for up to 5 minutes, followed by a tsunami that will wreak havoc along the entire northwest coast. Under pressure from Juan de Fuca, the edge of the stuck plate of North America is bulging upward and compressing eastward at the rate of respectively 3 to 4 millimeters and 30 to 40 millimeters a year. And sooner or later, North America will rebound like a spring.
It's the sort of same rate that your fingernails grow. So it's happening just very, very gradually. But so when they look at these rates, that's how they know how sort of stuck the subduction zone is, right? So they know how fast the plate is moving offshore, but then they know that it's stuck together once it runs into the subduction zone. So year by year, you're accumulating, oh, it should have moved this much, but it didn't because they're stuck together. And oh, it should move now this much because they're stuck together. At some point, it has to move that much. And it's just a matter of when, but it's building up and building up and building up. And eventually it's going to release all of that energy. It's just a matter of when.
Megathrust earthquakes aren't the only danger posed by the region. Roughly 60 miles from the west coast, the snow-capped peaks of the Cascade Range are part of an 800-mile chain of volcanoes, which extends from Northern California to southern British Columbia. The volcanoes are born from the slow slide of dense oceanic crust as it is pushed beneath the North American plate. The subduction releases water and melts overlying rock, resulting in a volcanic zone that contains well-known landmark volcanoes and approximately 2,900 other volcanic features, ranging from small cinder cones to substantial shield volcanoes.
So there's a lot of excitement and interest in supervolcanoes like Yellowstone and the potential that they could really erupt in a catastrophic eruption, which has happened in the past. But that is pretty infrequent, even geologically speaking. What's more likely to happen on a human length scale is that one of the Cascade volcanoes will erupt. The Cascade hosts 11 of the 18 very high threat volcanoes as classified by the USGS. And so they look both at the geologic history of the volcano as well as the population that would be impacted by an eruption. Some of those volcanoes, Mount St. Helens has erupted a number of times in the last century. So there are a number of volcanoes that are interesting to keep track of, especially the ones that are really near population centers.
Within the Cascades, there's lots of interesting research going on, most of it with respect to the volcanoes that have a lot of earthquakes. And so Mount Rainier has a lot of earthquakes, Mount Hood has a lot of earthquakes, and Mount St. Helens has more earthquakes than any of the others in the Cascades. And so a lot of the research that we're doing right now is around Mount St. Helens and has to do with understanding that system better. And since Mount St. Helens, based on its previous volcanic activity, has more eruptions than any other Cascade volcano, we expect that that will probably be the one to erupt next. And so doing research on Mount St. Helens, we're really trying to understand what's going on within the volcano so that when unrest occurs next, we can be better prepared to assess the volcanic hazard and push that information out to emergency managers and the public in a timely manner.
Prior to 1980, Mount St. Helens had the shape of a conical, youthful volcano, sometimes referred to as the Mount Fuji of America.
We're directly over Mount St. Helens right now, and there is no question at all that the volcanic activity has begun. You can see smoke and ash pouring from the top of the mountain, especially on the north side of the mountain.
On May 18th, a violent, explosive eruption occurred that killed 57 people and caused the entire north face to slide away, leaving a 2-mile wide, 2,000-foot deep crater. The event was the most deadly and economically destructive volcanic eruption in the history of the contiguous United States.
There was the 1980 eruption, which we learned a lot about the volcano then, obviously. There was several dome-forming eruptions from 1980 to 1986. And there was repeated cycles that we were able to study in really great detail and understand what the personality of the volcano is. And then in 2004, we were actually able to use what we learned in the big 1980 eruption and then the subsequent eruptions in 1980 to 86 to do what I think was a really nice job of forecasting what was going on in the volcano and pushing out to the public and emergency managers what the expected range of possibilities were. So at Mount St. Helens, the type of activity that we're seeing is consistent with the magma chamber underneath Mount St. Helens actually recharging. This is really similar to what we saw in terms of the activity between the last dome-forming eruption in 1986 and 2004. We saw earthquakes that were in that area right above the magma chamber. So we're seeing that again, and Mount St. Helens is more active than any other Cascade volcano. So we expect that this is going to be the next volcano to erupt in the Cascades.
Scientists are slowly gaining some ground in terms of understanding the volcanic systems in the Cascade Range. The ability to predict future eruptions rests solely on evidence that includes the history of previous volcanic activity, earthquakes, slope deformation, and gas emissions.
There's lots of different things that we would look at and take together to figure out whether or not something was happening. I'm a seismologist, so I'm biased toward the seismic activity, but not so biased that I'm not going to go look at the GPS or ask our geodesy folks what's going on with their data streams, or ask the geologists, you know, what are the range of possibilities that have happened in the past at Mount St. Helens. And so we bring all of this stuff together to figure out what's going on ahead of time. We know more about Mount St. Helens than we do about a lot of other volcanoes in the Cascades, partly because it is very accessible now, having the north side of the volcano be wiped of trees like it was in the 1980 eruption. There's a lot of good exposures of rock to be had. In the Cascades, we have lots of trees, we have lots of undergrowth. It's hard to get into some of these areas and really see some of these exposures. And a lot of that geology is on display now, especially on the north side of the volcano. So we know a lot about what's going on at Mount St. Helens, not just now, but well back into the past.
600 miles to the east, research is being done at Yellowstone National Park that could be a model for better understanding the volcanoes of Cascadia.
It's difficult to compare and contrast Yellowstone and some of the Cascade volcanoes because the systems are so different. Yellowstone's system is so much bigger than anything else in Cascadia. The magmatic system has so much volume and so much heat that it's quite a bit different. But some of the lessons in terms of monitoring data we can apply. So how we might design monitoring systems to look at how the ground is moving up and down or earthquake shaking. We can test things out in Yellowstone perhaps, because there we know we're going to see lots of earthquakes. We know we're going to see lots of ups and downs of the ground. And then we can take the knowledge there and apply it to places in the Cascades that maybe aren't quite as active. So Yellowstone's a pretty good testing ground for a lot of volcano monitoring instrumentation.
But even with all this network and scientific studies in place, the ability to really understand Cascade is still quite unknown.
Right now, it does have an okay network. We've been able to build some of that information in, but there's big blind spots within the network right now.
That means we still don't have all the information to give the scientist an idea of when or where the next big earthquake or volcanic explosion might happen. Mount St. Helens is only one of several high-threat, explosive volcanoes in a region riddled with the effects of the Cascadia subduction zone. The U.S. Geological Survey has updated its volcano threat assessments for the first time since 2005. And several landmarks appear in the top 18 called very high threat because of what's happening inside them and how close they are to large populations.
Other high threat volcanoes are definitely in the Cascades, and Rainier comes immediately to mind because of the potential for lahars to impact communities around Rainier.
Mount Rainier is one of the most dangerous volcanoes in the world. Unlike Mount St. Helens, Rainier is not known to be particularly explosive, but it does pose an equally deadly hazard. The heat from an eruption will melt immense glaciers on Rainier's ice-clad summit, resulting in a massive rolling slurry of water and volcanic debris that will quickly flow towards the densely populated suburbs of the Seattle-Tacoma metropolis. Pyroclastic flows in large lahars can crush, bury, or carry away almost anything in their paths. The valleys on Rainier's slopes are perfect for lahar formation, one of the most poorly understood and exceptionally destructive volcanic processes. During the 1980 eruption of Mount St. Helens, approximately 3 billion cubic yards of material was deposited in the North Fork Toutle River Valley. Like Mount Rainier, Mount Hood is prone to violent lahars and pyroclastic flows and sits on the doorstep of urban areas, including Portland, Oregon. In the recent past, Mount Hood has had two significant eruptive periods, one about 1,500 years ago and the other about 200 years ago. While not currently active, Oregon's signature peak produces frequent earthquakes, and steam and volcanic gases are emitted in the area around Crater Rock near the summit. In March 2019, after 140 years of dormancy, steam vents are starting to release from Mount Baker, which sits about 30 miles east of Bellingham, Washington. The rugged Cascade Range is home to several other potentially dangerous and active volcanoes: Mount Adams, Crater Lake, Glacier Peak, the most remote of the 5 active volcanoes in Washington state. The volcano is not prominently visible from any major population center, and so its attractions, as well as its hazards, tend to be overlooked. Yet since the end of the most recent ice age, this volcano has produced some of the largest and most explosive eruptions in the contiguous United States. Three Sisters. The most recent eruptions of Three Sisters were near South Sister about 2,000 years ago. However, in 2001, scientists recognized that a phase of uplift had started within a broad area west of South Sister. Newberry Volcano is the largest volcano in the Cascades volcanic arc and covers an area the size of Rhode Island. Mount Shasta. Hot springs and volcanic gases seep from the summit, indicating a relatively young and still hot system. Lassen Peak. In May of 1915, partially molten rock oozing from the vent began building a precarious lava dome. The dome collapsed, sending an avalanche of hot rock down the north flank of the volcano. 3 days later, a vertical column of ash exploded from the vent, reaching altitudes of 30,000 feet. While the threat of destructive volcano eruptions is very real, it pales in comparison to the devastation that will be unleashed by a megathrust earthquake. Great subduction zone earthquakes are the largest earthquakes in the world and are the only source zones that can produce earthquakes greater than magnitude 8.5. The Cascadia subduction zone has produced magnitude 9.0 or greater earthquakes in the past, and undoubtedly will in the future. If the entire Cascade Zone gives way at once, an event that seismologists call a full margin rupture, the magnitude will be somewhere between 9.7 and 10.2. That's the very big one.
Offshore, you have the subduction zone, so you have the North American plate, and then you have the Juan de Fuca plate that is sinking down beneath North America. And the Cascadia fault line is where those two are touching, and where the plates are, in fact, rubbing against each other. They're mostly stuck, and then occasionally when they let go, you get one of these very large megathrust earthquakes, and the plates slip.
Take a lot, we haven't heard.
Yeah, this is emergency in San Francisco. What happened? There's a hell of an earthquake, and we've got windows and everything is falling out.
When it releases, it will trigger a region-wide earthquake that will shake for up to 5 minutes, followed by a tsunami that will wreak havoc along the entire northwest coast. Worldwide, Subduction zone megathrust events are the largest earthquakes. In May of 1960, a magnitude 9.6 megathrust earthquake struck off the coast of Chile and lasted approximately 10 minutes. The event currently stands as the most powerful earthquake ever recorded.
Mountainous tidal waves triggered by the Chilean earth shocks raced across the Pacific at 500 miles an hour. Every Pacific island felt their colossal forces. On Hawaii, 6,000 miles distant, 60 are dead or missing, and damage in the Hilo area may reach $60 million.
Geologists have spent over 30 years piecing together a history of these megaquakes. Their conclusion? Cascadia has unleashed a magnitude 8 or greater quake every 244 years on average. And the last one was more than 300 years ago. Scientists say there is a 1 in 3 chance that Cascadia will strike within the next 50 years. When, not if, the next great Cascadia subduction zone earthquake strikes the Pacific Northwest, Oregon will face the greatest challenge in its history. Buildings, transportation network, utilities, and population are simply not prepared for such an event. Were it to occur today, thousands of people in the Northwest would die, and economic losses would be at least $32 billion. Scientists believe the next Cascadia earthquake has the potential to be one of the largest on the planet. Oregon is a geologic mirror image of northern Japan. In both places, the Pacific Ocean floor is sliding beneath the adjacent continents along giant faults called subduction zones. Oregon doesn't have to imagine what the next great earthquake will look like. In March of 2011, a 9.1 magnitude megathrust earthquake rocked northern Japan and triggered a tsunami that killed 15,000 people and wiped entire towns off the earth. Waves up to 6 feet high impacted coastlines as far away as Alaska, Hawaii, and Chile. As far south as Antarctica, nearly 50 square miles of ice broke off the Sulzberger ice shelf, resulting from waves generated by the Tohoku earthquake and tsunami. Seismologists have been studying this and say it is a matter of chance that Japan, not Oregon, got hit this time.
If you were on the coast today, because we don't have earthquake early warning yet in the state of Oregon, the first warning you would have of an earthquake would be that you would feel it. And the first thing you should do is just duck, cover, and hold on. And I often tell people in the community, start counting. If you have a magnitude 9 earthquake, it doesn't occur all along the Cascadia subduction zone instantaneously. It starts at one location and it unzips like a zipper. And because it does that, it takes time for that earthquake to develop. So the Cascadia subduction zone is about 1,100 kilometers or 600 miles long. And that rupture front expands at about 3 kilometers per second. So if you divide 1,100 by 3, you end up with, 5 minutes roughly for that earthquake to develop. If it's a smaller earthquake, like if we were in the room right now and there was a magnitude 4, it's over in a matter of a second or two. So when you feel an earthquake, the first thing you ought to do is duck, cover, and hold on. Start counting. If you're done counting by 10 seconds, that's not the really big one. If you're done counting in 30 seconds, well, that's a magnitude 7, magnitude 8 earthquake. If you're counting for several minutes, then that's a magnitude 9. From our point of view, we're more concerned about building of critical infrastructure in the tsunami zone. You don't want your hospitals in those regions. You don't want your police and your firehouses in those regions because those people are coming to save you after the earthquake. And if their fire trucks and buildings and personnel are in the tsunami inundation zone, then they're not there after the earthquake and tsunami. Schools, for example, shouldn't be built in those regions. Why would we put our children
in a school in a tsunami inundation zone when we could spend a little bit more money and move it up the hill. And so this gets to the issue of it does cost a little bit more to relocate your infrastructure or to choose locations that might not be central to your community. But from the point of view of eventually some event is going to happen, I think it's best to think of the highest priorities or the critical infrastructure you have and protect those buildings. Families and homes really ought to be 2 weeks ready pretty much anywhere in the U.S. because while we may have earthquakes here, another community in the Midwest may have another natural hazard where they need to have, basic water, food, and shelter to think about if something happens.
Just as happened in Japan, within a half hour of the earthquake, the tsunami would rush onto the land, more like an ever-growing tide than a normal wave. Anyone who doesn't manage to get inland or to higher ground in time would be unlikely to survive. The tsunami will devastate hundreds of miles of coast. In total, more than 50,000 square miles will be affected by the earthquake.
So I communicate to people about that because when you have something like a magnitude 9 earthquake, people can feel overwhelmed by the capacity for destruction that might be. And sometimes they can become immobilized by that. And I think it's very easy for them to start thinking in smaller steps. Do I have water? Do I have dry goods? And what would I do for shelter? The next thing we try to communicate to the public is simply that we don't know when the earthquake's going to happen. We know that it will sometime in the future.
We cannot avoid the future earthquake. It will likely result in grim damage and losses in a society diminished for a generation.
Our hope is it's in the distant future and that we need to start reconsidering our built infrastructure. Where does our water come from? How is our power generated and transmitted? Are our bridges safe? Are our critical infrastructure buildings that house first responders and schools, are those safe?
We are facing a very real and very imminent ticking time bomb right here in the USA. The shaking from the Cascadia quake will set off landslides throughout the region. Seattle's Emergency Management Office estimates up to 30,000 of them in the city alone. It will also induce a process called liquefaction, whereby seemingly solid ground starts behaving like a liquid to the detriment of anything on top of it. 15% of Seattle is built on liquefiable land, including 17 daycare centers and the homes of some 35,000 people. So is Oregon's critical energy infrastructure hub. 90% of the state's liquid fuel flows through a 6-mile stretch of Portland, in an area that also houses everything from electrical substations to natural gas terminals. Together, the sloshing, sliding, and shaking will trigger fires, flooding, pipe failures, dam breaches, and hazardous material spills. Any one of these disasters could swamp the original earthquake in terms of cost, damage, or casualties. 4 to 6 minutes after the dogs start barking, the shaking will subside. For another few minutes, the region, upended, will continue to fall apart on its own. Then, the wave will arrive, and the real destruction will begin. Every day, all day, just out of sight of Seattle, Washington, and Portland, Oregon, the ocean rises up and collapses, spilling foamy, overlapping ovals onto the shore. 80 miles away, 10,000 feet below the surface of the sea, the hand of a geological clock is somewhere in its slow sweep. All across the region, seismologists are looking at their watches, wondering how long we have until geologic time catches up to our own.